two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Let's consider these events and see if they're independent. So event A is flipping a fair coin, event B rolling a fair dice, rolling a 5 on a fair dice. These are independent events because flipping that coin doesn't affect the dice magically. Flipping a fair coin and flipping the same coin a second time, those are also independent events because the result of the first coin flip doesn't affect the result of the second. It doesn't suddenly make the coin biased. Taking a card at random from a deck of cards, taking a card at random from the deck without putting the old one back. These are not independent events because the card that you've taken, when you take the next card, the card that you took before cannot be taken again. So it does affect the second event. Taking an M&M from a bag, taking another M&M from the bag after eating the first, those are not independent because again, the M&M that you've eaten now has a 0 probability of being chosen the next time. Taking a card at random from a deck of cards, taking another card at random after putting the first one back, those are independent events. Because you've replaced the card, it effectively replicates that first event, so they are independent. The AND rule is for a sequence of independent events A and B. Essentially, the probability of A and B happening is probability of A times the probability of B. This is for independent events A and B, which is usually what we'll see at GCSE, with some exceptions. And essentially means multiply at GCSE. You can also write it like this, and it's very independent for it's very straightforward for independent events, but when they're not independent, when they're dependent events, there's a couple more caveats which we won't deal with right now. Here's an example. So we've got independent events here. I have a fair coin and a fair die. If I flip the coin then roll a die, what is the probability that the coin shows heads and I roll a 6? So I'm going to write my probabilities in words first. So I've got probability of H and 6. That's going to be the probability I get H or heads times the probability I get a 6. The chance I get a heads on a fair coin is 1 out of 2, 1/2. So I do 1/2 times, and then the chance that I get a 6 on a dice is 1 out of 6. It's 1 out of 2 times 1 out of 6, which is 1 times 1, which is 1 over 2 times 6, which is 12. The probability I get tails and I roll a 4. Again, 1/2 times 1 over 6, which is 1 over 12. The probability the coin shows heads and I do not roll a 3, well, the chance that I get heads, my first event, is 1/2. So it's 1/2 times, well, how many ways can I not get a 3? 5. So it's 5 out of 6 that I don't get a 3. So I would have to do 1/2 times 5 over 6, which is 5 over 12. Here's a question for you to have a go at. Please pause the video now and have a go, and when you're ready for the answers, press play. Here are the answers. So firstly, what is the probability I choose 2 yellow counters? Remembering that I'm replacing the counters, so I want probability of yellow and yellow. This is going to be, the chance that I get a yellow is 5 out of however many I have. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 counters. So it's 5 out of 12. And then another yellow counter, 5 out of 12. This is going to be 25 out of 144. Calculate the probability I choose a green counter and then a red counter. So the chance that I choose a green is 1, 2, 3, 4. So it's 4 out of 12. And then the chance that I then choose a red is 3 out of 12. So it's 4 out of 12 times 3 out of 12, which is going to be 12 out of 144, which simplifies to a 12th. Notice here, I'm not asking you what is the chance of getting a green and a red, because if that were the case, I'd also have to factor in the chance of getting a red and then a green. But we're not interested in that just yet. Well, actually, So events which cannot occur at the same time, these are mutually exclusive events, and it's really nice to look at this as a Venn diagram. So I'm either asleep or awake, it can't be both. A light is on or off, can't be both. It's either snowing or not snowing, can't be both. So these are examples of mutually exclusive events. And for mutually exclusive events, we have probability, so if A and B are mutually exclusive, probability of A or B is the probability of A plus the probability of B. And if you look at a Venn diagram of the situation, it makes it a little bit easier to think. Mutually exclusive events have no overlap, so to work out the chance of A or B happening, you just do probability of A plus the probability of B. This is the OR rule. OR means add, as far as we're concerned. So here's an example. I roll a fair die. What is the probability I roll a 4 or I roll a 5? Well, one way that you could think about this is probability of 4 or 5. Because it's impossible to get two different scores when you roll a dice, these are mutually exclusive events. So it's basically the probability I get a 4 plus the probability I get a 5. The probability I get a 4 is 1 out of 6. The probability I get a 5 is 1 out of 6. So we can say it's 1 out of 6 plus 1 out of 6, which is 2 out of 6. Remember, we add the tops, not the bottoms. Secondly, I either have porridge, cereal, or toast for breakfast. The probability I have porridge is 0.4. The probability I have toast is 0.3. What is the probability I have porridge or toast? Again, these are mutually exclusive events with no overlap, so that's just going to be 0.4 plus 0.3, which is 0.7. Now, the only options for this person's breakfast is cereal, toast, or porridge. So if the chance they have porridge or toast is 0.7, and probabilities add up to 1, exhaustive probabilities add up to 1, and the probability they have cereal has got to be 0.3. Here's a question for you to try. Please pause the video now and have a go, and when you're ready for the answer, press play. Here's the answer. So, the probability that Kelly walks or cycles to work is going to be 0.2 plus 0.7, which is 0.9. What is the probability she takes the bus to work? Well, if the chance that she walks or cycles is 0.9, and exhaustive probabilities add up to 1, the chance that she takes the bus to work, assuming there are no other options, it's got to be 0.1, because that's what I'd have to add on to get 1. We also have mutually inclusive events. So this is really only if you're studying the higher, so this is really only for the higher exam. So mutually inclusive events do have an overlap. So there's a special OR rule for this. It's unlikely that you're going to get this in a question, but it could possibly happen. And essentially what we're looking at here is the probability of A or B happening. So as we saw in the Venn diagrams video, we can use the union notation for this. The probability of A or B happening, or both. So that's represented by everything inside the circles that represent the sets. You've got to think of the different ways that we could have this. If you're inside these circles, you could be in the A circle, so that's essentially probability of A, or you could be in the B circle, so that's probability of B. But the thing is, if you add up probability of A, so if you consider the A circle and you consider the B circle, if you just add up probability of A and B, you should notice that the overlap has been shaded twice, right? It's been shaded, you can see red and green in it. It's been shaded twice. So in order to just have the probability of A or B or both, we need to subtract that overlap so that it's only actually shaded in the once. So the probability of A union B is probability of A plus probability of B, take away the probability of the intersection. So basically, probability of A or B is the probability of A plus the probability of B, take away the probability of A and B. And just very quickly, you should remember the probability of A and B for mutually exclusive events was 0 because it didn't have any overlap. So we were really using this rule before. It's just that probability of A and B was 0, so we just didn't think about it. Let's have a look at this in a question. So let me just type it out for you there. So probability of A or B is probability of A plus probability of B, take away probability of A and B. Example, in ysgol gobaith, the probability of people owning a phone is 0.8, probability they own a tablet is 0.1, probability they own a phone and a tablet is 0.1 also. Calculate the probability they own a phone or a tablet or both. So to do this, we could say that P is the event that they own a phone, T is the event that they own a tablet. So I need to work out probability of P union T. So that's going to be the probability of P plus the probability of T, take away the probability of P and T. So probability of P is 0.8, probability of T is 0.1, and the probability of P and T is 0.1, so we take away 0.1. This gives us an answer of 0.8. So the chance that they own a phone or a tablet is identical to the chance that they own just a phone, because in fact if we drew this out as a Venn diagram it would actually look like this. So there's P, there's T. If we think about putting the probabilities into the Venn diagram, the chance of the intersection is 0.1. and the chance of owning a phone is 0.8, so we need to have 0.7 here, and so that the full circle for phone is 0.8. And then if you look at the chance of a tablet, chance of owning a tablet is 0.1. There's actually nothing to fill in outside of the intersection for T. So that means everyone that owns a tablet automatically owns a phone because they're in the intersection. Here's a question for you to try. Please pause the video now and have a go, and when you're ready for the answer, press play. And just to note, you can use the formula that we've worked out for mutually inclusive events. You can also draw a Venn diagram, that might be preferable. Here's the answer. So we can draw a Venn diagram if we want, so CG for computer games, TV for TV, obviously. And you can also just think of it with the formula. Probability of computer games or TV is probability of computer games plus probability of TV, take away probability of computer games and TV. So we should end up with 0.75 for the chance that he watches TV or plays computer games or both. And also you could look at the Venn diagram. So filling in the Venn diagram, we can see if we fill in the middle first, 0.4. To make computer games 0.65, you've got to have 0.25 here. And to make TV 0.5, you've got to have 0.5 out there. So we could use the Venn diagram if we wanted to, or we could use the formula. If you use the Venn diagram, you just have to add up the three numbers. 0.25 plus 0.4 is 0.65, plus 0.1 is 0.75.